In this video, we're going to solve a particular problem which appeared in the year 2019. In this problem, we have a given function fx and divided into different region, x less than 0, 0 to 1, and so on and so forth. And we have to find which options are correct. Now here, to test this, we need to find out, right, that derivative. Why? Because notice that here we have if dash x has a local max mean, then it's increasing or not. So these options need to be selected in. So that's why we have our first job is to differentiate and then we have to analyze. So let's go ahead and solve this particular problem. We have to already discuss that we have to differentiate it, right? So first we consider the definition of the function for x less than 0. Now for x less than 0, right, the fx is a polynomial, x to the power 4, 5x4 and all that stuff. Now this particular thing, right, can be easily differentiable, right? So let's do the differentiation. So if I perform or apply the differentiation, this 5x to the power 5 will become 5x to the power 4. This will be 20x cube, then 30x square, then 20x plus 3, and everything will be added by plus sign, right? That's it. So let's go ahead and write down the expression of f dash x by differentiation. Now see that everything have a 5 common except that 3. So this 3 can be written as 5 minus 2, and then we take that 5 common from all the first few terms, right? So therefore if we do so, we get it as 5 into some expression minus 2. Now notice if I substitute x is equal to plus 1, we don't get any solution. But if I substitute x equal to minus 1, it will be minus 1 minus 4, plus 1 minus 4 plus 6 minus 4 plus 1, right? So therefore plus 1. So therefore we can see that, right, it will gives you, right, the 0. So therefore we say that x plus 1 is a factor. Now as x plus 1 is a factor, so therefore we can easily rewrite as x to the power 4. Now see, x plus 1 is a factor. So to do so, we need to take x cube common so that we have x plus 1 as a factor. So therefore we have to write x cube here. What's the term? 4x cube. So I write 3x cube here, right? Now to get x plus 1 factor, we get 3x squared common. So therefore we'll have x plus 1. Now 3x cube plus 3x squared. So 3x squared needed here. 6x squared is present. So I have to write 3x squared here. Again, I take 3x common. We'll get x plus 1. So now 3x squared plus 3x. So 3x. Now here we have x, right? So x plus 1. So see that the last we get x plus 1 common. So this method is easy for factorization, right? That's it. So now let's rewrite it. So therefore, we rewrite the decomposition of the function and take x cubed common from first few terms. And then we get it as 5 into x plus 1 into x cubed plus 3x squared plus 3x plus 1. And the term inside the curly bracket will be x plus 1 whole cube, right? And therefore, it will be 5 into x plus 1 whole to the power 4 minus 2. So therefore, f dash x will be equal to 5x to the power 4 minus 2. So that's it. So just note down that definition for f dash x when it is lies between minus infinity to 0. Now we have to differentiate the remaining. So now we consider the definition of the function between 0 to 1, which is fx equal to x squared minus x plus 1. After the differentiation, it will be 2x minus 1, straightforward. We consider the definition of the next case, that is minus 1 to 3, and in that case it will be 2 by 3x cubed 4x squared plus 7x minus 8 3, and by differentiation it will gives us, right, that f dash x is equal to 2x squared plus minus 8x and plus 7. That's it. Now only we have left one more differentiation we need to perform, that is x greater than equal to 3. Consider the definition of the function for x greater than equal to 3, and now we have to differentiate. Now see that here two functions are multiplied, so therefore we need to apply that UV method, right, the product rule, right? So therefore it will be, if I write that d dx of x minus 2 will get 1 into log of x minus 2 will be as it is, plus x minus 2 will be as it is, and differentiation of log x minus 2, that will be 1 by x minus 2. Minus x will be minus 1, and 10 by 3 will be omitted. So therefore, we rewrite that f dash x directly. And hence, f dash x will be log of x minus 2 plus minus 1, which gives me log of x minus 2, and that's it. So therefore, we find out that if x lies between 3 to infinity, what is my f dash x? For option A and C, it is given that f dash has local max or not, right? And f dash is differentiable or not. That means we need to test it, f double dash x, right? So let's calculate the f double dash x by directly differentiation f dash x with respect to x. So if we do so, f double dash x, right? So that's why we first consider that the interval minus infinity to 0, where f dash x is equal to 5x whole to the power 4 minus 2. So if I differentiate, it will be 20x plus 1 whole cube, right? Direct chain rule application. 0 to 1, it will be 2x minus 1 differentiation, 2x. For 1 to 3, it will be 2x square minus 8x plus 7, which gives me 4x minus 8, and that's it, right? So the last one, differentiation of log x minus 2, will be 1 by x minus 2 in the interval 3 to infinity. So therefore, we get it as 1 by x minus 2. That's it. So all the derivative we calculate. Now we need to find the local maximum, right, at x equal to 1. How we test the local maximum? For that, we need to find that x equal to 1 is a critical point or not. So that means we have to take f double dash f dash x is equal to 0. Now see that approach for finding critical point is not there, right? Because if dash x is 0, what will be the value, right? Definitely you can see that at if dash x as 0, right? At 0 minus 1, so undefined and all that stuff, right? So it's minus 1, right? So if we see that, right, put x equal to 0 at this definition, we'll get it as minus 1. So if double dash of 0 is not equal to minus 1. So therefore, it's not a critical point in the normal approach. But also, we know that critical point means that in that particular point, f double dash x may not exist. If not exists, it's a critical point. So here we can test that part as well. So here we have to think that as is if double dash x exists, because now we have to concentrate that f dash x and that derivative, right, is exist at x equal to 1 or not. So that's why we concentrate on the definition of f double dash x. Notice that here I mark the point x equal to 1. 0 to 1, it is 2. And then it's a straight line, 4x minus 8. I don't draw it with a proper sketch, okay? Then you have to draw that, right? I just saying that, put the definition at that area. Now let's go ahead. So now here we try to evaluate the left limit, left derivative of f dash x, or that means that f double dash at 1 minus. So at 1 minus means this region, it is definitely 2. So we'll substitute x equal to 1 at f double dash x equal to 2, which gives me the left derivative as 2. To find the right derivative, we need to substitute x equal to 1 in the definition of 4x minus 8, which gives me 4 minus 8, which gives me minus 4. So from here, we conclude that right and left derivative for the function f dash x, right? For the function f dash x doesn't exist, right? Because it's not equal. So therefore, f dash x is not differentiable at that particular point, x equal to 1. And hence, option C is correct. So we are trying to test for option A, but we already get that option C is also correct. Now let's go ahead. Now already seen that if dash x is not differentiable at x equal to 1, hence x equal to 1 is a critical point for if dash x, though if dash 1 is not equal to 0. Now, as it's a critical point, right? So therefore, we have to test it is maximum or minimum, right? That's it. So now let's go ahead and substitute x equal to 0.5. Why? Because here we just draw a 1 point. I take 2.0.75 in the left hand side in the neighborhood of 1, right? And if I substitute x equal to 0.75 in f dash x, we get it as f dash of 0.75 is equal to 0.5, which is greater than 0. So therefore, f dash has positive sign here. Okay, f dash x has positive sign, and we need to calculate what the value happens afterwards. So for to calculate that, we substitute x equal to 2 here, right? And if we calculate, we get that it is -1. So that means it is negative sign. Okay, so what happened then? So we can see that, right, for this particular case, right, if we trying to sketch the function, right, at 1, at 0.75 is greater than. So therefore, from 0.75 to 1, f dash x for the phase f dash x is an increasing function. And then f dash 2 is less than 0. So that function will be uh, decreasing function. So therefore, at x is equal to 1, we definitely have a local maximum. So therefore, as the function of f dash x, or the value or the sign of f dash x changes from positive to negative, it has a local maximum at x equal to 1, and thus option A is correct. So two option is already selected and which are treated to be correct. Concentrate on option number B. Here it says f is increasing. Now, f is increasing means that in the interval minus infinity to 0, that means f dash x must be greater than 0 entirely in the interval minus infinity to 0. Now, here we consider, right, the definition of f dash x. Now, notice that, right, if I substitute x is equal to -1, right, it's negative. So therefore, if I put x equal to -1, if dash of -1 is negative, which states that, right, that fx cannot be an increasing function, right, inside the interval minus infinity to 0. So therefore, option B is not correct. Now we need to find out or test the last option, which is onto. Test the ontoness. We can find out by normal approach that range and domain of the function are equal, right? That's it. Let's go ahead. Range and domain are equal, so then it will be an onto function. Okay, let's go ahead. So here, to find out the domain, right, here we notice that when x is less than 0, it is a polynomial. 0 to 1, it's a polynomial. 1 to 3, it's a polynomial. So therefore, we can say that fx is represented by different polynomials at minus infinity to 3, and it's all the polynomial are continuous. So therefore, fx are well exist or well defined in the interval minus infinity to 3. Also, you can see that when x is greater than 3 or in the interval 3 to infinity, fx are defined by log. Now, log of x minus 2 is already undefined when x is less than equal to 2, because then it is a negative value. But so that's why when x is greater than 3, the function fx is well defined. So therefore, we can say fx is continuous and well defined in the interval minus infinity to plus infinity. So therefore, the domain of the function is a real number. Domain. Now our job is to obtain the ranges. Now see that between 0 to 3, right, when we talk about the function as x squared this and these three, sorry, not the last one, that x square minus x and 1 to 3, right, that definition, right? So these are polynomials, right? So it may have a upper limit or lower limit, that's okay. But x to the power 5 and x minus 2, that definition of, well, x less than 0, x greater than equal to 3, we can apply the limit to tends to infinity, so that we can test is there any fixed upper bound or fixed lower bound, right? So that's why we take the limit, right? Limit x tends to in minus infinity fx, right? Now when x tends to minus infinity, we have to take the definition of x less than 0. Now here we need to apply that. So see, x to the power 5 is the largest power. Take that power common. And we just rewrite that by the product of two limits. Now when x tends to minus infinity, 5 by x, 10 by x square, all the stuff will convert it to 0. So therefore, the second limit will be equal to 1. So therefore, it will be equivalent to x to the power 5, and which will be equal to minus infinity. So therefore, the function, we have the no lower bound. So it is bounded, not bounded from below. So if we plot the function, right, there will be some value in this any region below, right? That's it. Let's go ahead. check the behavior of the function when if x tends to plus infinity fx. So in that particular case, right, we need to apply the limit. Now here we take y equal to x minus 2, which gives that y tends to plus infinity y log y plus x tends to infinity minus x plus 10 by 3, right? That's it. Now notice that here log y. So we know that minus x, right? So this minus x, right? X tends to plus infinity minus x. It's a linear way. It will the x value will increase. But here we have y multiplied by log of y. So this function will increase very faster that corresponding to the way where minus x will decrease, right? So therefore we'll say that the rate of increase of y log y will be much higher than the minus x. So therefore we'll say that log of limit of x tends to plus infinity fx will be plus infinity. So we take the function have values from minus infinity to plus infinity. That's why the range of the function is also minus infinity to plus infinity. And hence, the function domain and range are same, and hence it's a onto function. So therefore, option D is correct. And that's it. So therefore, for this particular problem, we have three correct options, A, C, and D. B is the only wrong options. And that's it. Hope you understood the problem. So it's just a analyzation of the function of fx, f dash x, and f double dash x by normal differentiation. So it's looks very lengthy, but it's not actually if you think carefully. It's all that how much time you take that differentiation, which just take 1 minute, and the analyze take 1 minute, and that's it. Hope you understood the problem. Thank you.